All right. Hello, everyone. For those of you who are watching this later on, we're going to do some problems from chapter 13. We've now gotten into the calculus section. Very exciting. But before we do that, I want to start off with a general kind of problem, something that we have to do periodically. And if you're taking 230 and not 231, you're definitely going to have to do this a lot towards the end of the semester. So I want to sort of get used to thinking about this now. And it's this issue of curves of intersection. So if you've got two surfaces, so the general problem that I want to look at is you've got two surfaces. And you want to find a parametric equations or perhaps a vector function. They're basically the same thing as we saw with lines. For the curve of intersection. And the image that we should have in our mind is something like this, where you've got one curve, you've got one surface. I'm going to draw it in blue. Right? But meanwhile, you have another surface, which I'm going to draw in red. And these two surfaces intersect in some line, and I don't know, or some curve, and I don't know what that curve is necessarily, but that's what we're trying to look for, right? We're trying to look for this curve of intersection. That's our main goal, is to find that, find this curve of intersection. So find equations for this curve. And this is sometimes kind of tricky. This often requires a little bit of creativity to figure out what exactly that curve looks like, but there are usually some standard tricks that you can use to do this. So for example, let's move along. You can take, let's do an example of this. What if we have the cylinder given by x squared plus y squared is equal to 4. And we want to intersect that with the surface z equals xy. And what is that curve of intersection? Now, one common trick is circular cylinders have a nice representation. You're going to use the fact, in other words, that the circle x squared plus y squared equals a squared for some a, in this case a is 2, can be given by, that can be given by x equals a times cosine t and y equals b times sine, is equal to a times sine t. And we're going to use that here. We're going to use that trick in this case, because keep in mind that what do we really need? What we need, and this is the important thing that we should be paying attention to right now, is what do we actually need? What we need are functions that are given by x equals, I don't know, I'll call it f of t. Y is a different function, I'm going to call it g of t. And z is a different function, I'm going to call that h of t. So that f, g, and h, so x equals f, y equals g, and z equals h, satisfy both surface equations. for every t. And that's really what we're looking for here. Now, the reason this trick works is that we can do that immediately with the first equation. We can do that immediately with the cylinder by letting, we're going to say that x is, using this trick, x is going to be 2, and y is going to be 2 sine t. And that satisfies the first equation completely for every value of t. But what about the second one? We now need to worry about the z equals xy business. How are we going to take care of that? Well, it's quite simple. Now that we know what x and y are, follows that since we have to have z equals xy. That's not negotiable. That's what we've been given. We get z is equal to 4 sine t cosine t. So the upshot of all of this as our final answer is that r of t is equal to 2 cosine t, 2 sine t, and 4 sine t cosine t. So that, I claim, is our final answer. And how do we do this? Well, we used our, the first thing that we did is we used our cylinder equation and our trick to get x and y. So that was the first step. And we already know what z should be. We have z coming from the second equation, and that just automatically gives us the second z. And it follows, in that case, we can just look at this, that this satisfies. So these x, y, z functions both of the original equations, x squared plus y squared equals 4, and also z equals xy. And if you're not convinced of this, then I can show you how. If you go into GeoGebra, let me do that right now, if I can find it in the sharing things. Where is it? It's somewhere in here. Yes, here it is. If you go into GeoGebra, what you can do, here's how you can check this. So you can create your two surfaces. Our first one was x squared plus y squared equals 4. And that gives us our vertical circular cylinder of radius 2. We see that. But meanwhile, z equals xy. And I'm going to color that differently so you can see that these are different different objects. I'm going to color this, I don't know, color green. Right? So we've got two different objects here. We've got on the one hand this this hyperbolic paraboloid given by z equals xy, but we also have the cylinder, x squared plus y squared equals 4. And if you take them both together, you can intersect F1 and F. That doesn't like that at all. Okay. Intersect equation 1. Sometimes you got to play with it a little bit. And z equals xy. Doesn't like that either. Okay, intersect x squared plus y squared equals 4, and z equals xy. Why not? Why don't you like any of those things? Let me try something else. Xy equals z. No, that's not what I wanted. Okay. So maybe I can't do it that way. That's fine. I'll make this work anyways. The point is, you can see the curve of intersection inside of the cylinder. It's kind of hard to look at, but you can see that it's there. And here's how, well, I know this will work. Here's how you can plug in a curve in GeoGebra. You got a curve, and the curve that we thought it was, the curve that we conjectured this should be, was 2 times cosine of t, 2 times sine of t, and 4 cosine t sine of t. We believe that's what it should be, and our parameter is t, and let's say that t is going from -10 to 10 and see what happens. And aha, the curve is this sort of bendy loop, and we can see it's precisely at the curve of intersection. So we were right. This is exactly the curve that we want. Good. Very good. Okay. So with all that in mind, we can keep going. What if we, let's do a different example. Let's take, for example, let's say we want to look at 4x squared plus, so we want to look at z equals 4x squared plus y squared, and y equals x squared. And again, we want to find the curve of intersection. Okay? Now to do this, what we're going to do is we're going to make a couple observations. Here's the trick. Again, here's the different trick we're going to use in this case is that the second equation, the second surface, has y as a function of x. So suppose, for example, that we take x equals t. Say x equals t. Why are we saying x equals t? Well, just hold on for a second. You'll see why this works. X equals t. And if x equals t, y equals x squared, it follows that y has to equal t squared. That certainly satisfies the first, the second equation. No question about that. But if that's the case, then again, we can say going from the z equation, we know what x is, we know what y is, so we just have to find out what z should be. So it follows that z is going to be what? Well, it's going to be 4t squared plus y squared, or in other words, t to the 4th. So we're going to get r of t is equal to t squared, t to the 4th plus 4t squared. Oh, whoops. I'll try doing that in a way that doesn't cut through my final answer. Or you can equivalently write this as x equals t, comma, y equals t squared, comma, z equals t to the 4th plus 4t squared. These mean the exact same thing. These are completely equivalent ways of expressing this. The nice thing about the second way, this second strategy in this case, we can see here that x and y certainly satisfy the first of these equations, but they also have that z, in that case, must satisfy the second equation at the same time. That's the benefit. We can see that x, y, and z all satisfy both of these equations. That's basically the way to find these curves of intersection. Let's do another one. Let's say that we have, let's do another example of this. Find the curve of intersection of, I don't know, let's say we're going to take x of x squared plus z squared equals 1, and x squared plus y squared plus 4z squared equals 4, with the stipulation that y is greater than or equal to 0. Now, there's a little bit of a trick here. The trick is that if you, or not a trick exactly, but something we want to be careful of. Let's look carefully at this surface. That right there, we remember that that's an ellipsoid. And over here, we have a circular cylinder. Meaning, this is what this is going to look like. You're, on the one hand, actually, I'm going to write this in, going to draw the second of these in a different color to make this a little more clear. I'll make this pink. So, so here we have the circular cylinder. So what does this look like? Well, you've got your ellipsoid, and in this case, it's going to be a little more skewed in the XY direction, so it looks a little bit like this sort of disc thing. Not disc, but sort of like this long oblong oval, right? Something like this. So you've got your circular cylinder. But meanwhile, you also have, this is not to scale, but you also have a cylinder that's cutting through it, right? The cylinder that's cutting through it has two different curves of intersection, right? So if we look carefully, what we notice here is we've got two different curves of intersection, right? 1 and 2 for this surface. Which one are we interested in? Well, the answer comes into the fact that we have y is greater than or equal to 0. So we really only care about this piece on the right side, because that would be when y is greater than or equal to 0, presumably. So that's the piece that we care about. That's what we're going to find the curve of intersection for. And that's going to become important as we consider what happens with the algebra here. First of all, we can still use our same trick from before, except we're going to use x and z instead of x and y. So with this cylinder, we can still say that x is, in this case, cosine of t, and z equals sine of t. By the way, you can flip the sine and cosine without a problem. You can say x equals sine of t, z equals cosine of t, but you end up flipping what's called the orientation. That is, you're going in the opposite direction as you go around that circle. If you're taking 231, that doesn't matter. If you're taking 230, orientation is going to matter a lot more towards the end of the summer. So x is cosine t, z equals sine of t. So that's that object. Now we have x and z. What about y? Now here's the thing. We don't have y as a function of x and z anymore. So the best thing that we can do is go from our ellipsoid equation. We know that y squared is equal to 4 minus x squared minus 4z squared, which in other words is 4 minus cosine squared of t minus 4 sine squared of t. You can clean that up quite a bit using the fact that that cosine squared plus sine squared is 1. So this becomes 4 minus 1 minus 3 sine squared of t. Or in other words, 3 minus 3 sine squared of t. Or even more in particular, if you really want to be nifty with this, that's 3 times 1 minus sine squared of t. Or in other words, 3 times cosine squared, if you really want to get fancy. 3 times cosine squared of t. Now, here's the thing. You got to be a little bit careful with this, because strictly speaking, you could have it be the case that this thing is negative, and that's not going to really give us what we want. So because we want y to be positive here. So what we're going to do, we've got x and we've got z, so y, we know what y squared is. Y, it turns out, has to be equal to the square root of 3 times the absolute value of cosine t. It's a little tricky. It's a little tricky in this case because you take the square root, but you need it to be positive. Well, square root of something squared is just the absolute value, so you just leave it as y equals root 3 times absolute value of cosine t. Still leaves you with x equals cosine t, and z equals sine of t. No issue. And that ends up being our final answer. It's a little tricky in this case, but you got to be careful with this y is positive. This is sort of a extra challenge subtlety in this particular problem. Now, if we were to do this in GeoGebra, this would look a little bit funny, as it turns out. So let's see what that actually looks like, just for fun. Let's see what this comes out to. So here in GeoGebra, here's our first equation, our x squared plus z squared equals 1, the cylinder that we knew before. We also have our ellipsoid. We knew that that was going to be x squared plus y squared plus 4z squared equals 4. You can see that on the right-hand, on the. But watch what happens when you intersect these things. If you intersect them, it's a little bit funny because the ellipsoid and the circle in the xz plane, those traces are tangent to each other, which means that they just barely touch at that point. So you have this weird sort of x in the intersection. Now we only care about y being greater than or equal to 0, so if you actually make the curve in the way that we expected, so we've still got x equals cosine t, y equals root 3 absolute value cosine t, and z equals sine of t. Here's what you get. You actually get this sort of half circle. You get a circle on the one hand, but it's only half of the ellipse in the other side. It's kind of weird like that, right? You got this weird cusp on that side, so it looks kind of funny in that sense. Okay, so now, going back to where we were. I want to do one more of these just to see how, just to see what different strategies are that we can use, because these tend to be some of the harder problems that people often have trouble with. So one more example of this. We can take z equals root x squared plus y squared, that's a cone, and z equals 1 plus y. Now here's now this one requires a little bit of creativity, because on the one hand, you've got your trick that z equals 1 plus y. So our trick from before could let us say that, okay, why don't we just let y equals t and z equals 1 plus t. What happens if we do that? Well, we still need to find out what x is, and x isn't so easy to find from the first of these surfaces. So what that would give us in that case would be that 1 plus t equals square root of, I don't know what x squared is, we'll work that out in a little bit, plus t squared. And we can still figure out, we can still kind of figure out what x is in that case. What does that give us? That gives us, now we can say that's going to give us that x is what? Well, let's find out. Square both sides, that gives us t squared plus 2t plus 1 is equal to x squared plus t squared after squaring both sides. Okay, well that means that x squared equals 2t plus 1. So x is plus or minus root 2t plus 1. And that's not super satisfying because, well, is x plus or minus? I mean, what can we say about that? Is there anything, can we do any better, in other words? And not really. That's about the best we can do, I think. Now, on the other hand, we could also, we can also give, here's an alternative strategy. An alternative strategy would be to say that root x squared plus y squared is equal to 1 plus y squared, because they're both equal to z. And what does that give us? Well, that's going to give us, again, squaring both sides. Sorry, not 1 plus y squared, just 1 plus y. Again, squaring both sides would still give us y squared plus 2y plus 1 is equal to x squared plus y squared. But the good news in this case, this is a little bit better, because now what we can say is that y, so the y squareds cancel, so y is equal to 1/2 x squared minus 1 after doing some algebra. Now that's actually better, because now what we can say, now we have y is a function of x. So now we can say from this object, from this bad boy over here, I feel like a car salesman. So we can now look at that and say, okay, well now we can say that x is t and y is 1/2 t squared minus 1. And that's much better, because now we can say that z, we know what y is, we know what z is. Z is 1 plus y, 1/2 t squared plus 1 after you do the algebra and the arithmetic. So our final answer in this case, I'll make it a little bit darker. So what we have here is the r of t that we want for this curve of intersection would be t, 1/2 t squared minus 1, 1/2 t squared plus 1. My point is, these kinds of problems involving curves of intersection, they often require a little bit of creativity. And we want to begin getting used to trying to do these now. Try to really get used to, especially if you're in 230 this summer, we want to start really practicing figuring out what these curves of intersections actually look like. All right. Now, curves of intersection are some of the things that we are looking at in this chapter, but as I said, we're now getting into the calculus, so I want to look at a different kind of problem. This is from section 13.2. The problem involves parametric equations for a tangent line. Now, every now and then we'll have students that'll just ask us, well, wait a minute, how do you find parametric equations for a tangent line? I mean, tangent lines are weird, right? You have to do calculus to find these things. And what's so weird about these things? How do you do this? What's the strategy here? And how is that different from the lines that we saw before? But it's not different from the lines that we saw before. For any kind of line, it all comes down to the same basic principles. So whenever you're trying to find a line, just remember, this is the most important thing here. So just the important thing to remember we need, first of all, a point on the line, and we need a direction the line is going in. And with tangent lines, we can basically find those two things without very much difficulty. So let's say, for example, if we just think for a second about what's actually going on. So let's suppose we take the curve x is equal to ln t plus 1. Y is equal to t cosine 2t. And z is equal to 2 to the t. And we want to find the tangent line at the point 0, 0, 1. By the way, as a reminder, that if you take the derivative of an exponential where the base is not e, so say you take the derivative of a to the t, that's just a to the t times the natural log of a. So we can use that for this problem. We're going to have to use that for this problem. So how are we going to do this? Well, just remember that really what we're considering here is some kind of line or some kind of curve, right? So suppose we've got some curve going off in space. We've got our point on the curve. What we really want is the tangent line at that point. So let's suppose that that's not well drawn at all. Suppose that if I'm very careful as I'm drawing this, that's what we're looking for, right? We're looking for the tangent line of that curve at that point. And that tangent line, well, let's think about that. We need a point on the line. We have a point. That's the point that we've been given. And we need a direction. But the direction of that, as soon as you start thinking about this for a second, we realize that the direction that we care about is just the tangent vector at that point. In other words, the point, let me put that another way. Uh-oh. I want to make it a thinner thing now. So the point is whatever the point that's given is. But the direction is the tangent vector r prime at that point. But you really have to find the direction vector at that point, and here's where a lot of students get tripped up. So in this case, we know the point is 0, 0, 1. We've been given that. What about the direction vector? Well, we need to know what r prime of t is to find that. R prime of t, in this case, we can just do the calculus here. That's not terribly hard. That's going to be 1 over t plus 1 I. In the j direction, actually, I'm going to do this on the next line down just so that I have some more room to work. So r prime of t is 1 over t plus 1 I plus, now you need to do this with the product rule here, right? So you've got cosine of 2t minus 2t sine 2t in the j direction, plus, and here we are going to use 2 to the t times ln of 2 in the k direction. And that, I claim, is our tangent, is our velocity vector at a given point, or at any point, but we need to find it at a very specific one. We need to find that at a point 0, 0, 1. Now the question is, what is this? So here's the new question that we should be asking ourselves. What is this r prime at the point 0, 0, 1? We can't just plug that in directly for the direction vector because you're going to have t's all over the place. That's not going to make any sense. We need a very specific, we've been given a very specific curve. We've been given a very specific curve at a very specific point. And that has only one very specific tangent line, and that tangent line can only have one very specific direction. That direction cannot have variables in it. So whatever we find for our direction vector better not have variables. So what is our velocity vector? What is our tangent vector at that point? Well, we need to know what t is, right? We need to know what the t is at that point. So we can observe that if we take t equals 0, well, t equals 0 is going to give us x equals 0. Y is obviously 0 because it's 0 times cosine of something. And then z is 2 to the 0, which is 1. So in other words, r of 0 is 0, 0, 1. That's our point. So what we need, really, is r prime of 0. R prime of 0, you plug that guy in, that's going to give you 1 over 1, or 1. The next term is going to be 1 again for the j term. And for the k term, it's 2 to the 0 times ln 2, so we're just going to get ln of 2. That's our direction vector. So the upshot of all of this is we're going to get, we have x equals now 0 plus 1 times t, so x is t. Y is again 0 times 0 plus 1 times t, so y equals t. And z is 1 plus t times ln 2. I claim that that is the tangent line at that point. Now let's see if we're right about this. Again, we can use GeoGebra to figure out if we did this correctly. So just give me a second. So the curve we've been given in this case, what was that? It was ln of t plus 1. And the y term was t times cosine of 2t. The z term was 2 to the t. And let's say that t is going from negative, well, actually, the smallest thing that t can be is negative 1, and that's a very strict lower bound. So let's say that it's negative 0.9. I think the smallest that t can be to 100. All right, and here's t. Here's the resulting curve. We can zoom out and see that that curve starts growing very large. And so with all, and you know, the y term keeps oscillating, but the x and the z starts flattening out at a certain point. What we really care about, though, is what is the behavior of this thing at 0, 0, 1. That's the point. The point, in other words, is right there at that point A. So that's where we want to know about our tangent line, and we believe that that tangent line is given by the curve, which we said was t, 1 plus t times natural log of 2. Let's see if we're right, and voila! We see that that line is, in fact, tangent to the curve at that point. So we were right. We were right. That is, in fact, the tangent line that we were looking for. Good. You can always check this in GeoGebra 2 to check your work, and that's one way of doing that. Okay. Let's do another example of this. Let's say that we have, oopsie. Let's say that we have, I don't know, what if we take as our next example, we can take, sorry, hold on a second. We can take, for example, x is equal to, where am I? I am at x equals root t squared plus 3. Y is equal to ln of t cubed plus 3. Z is equal to t. I'm going to find the tangent line at the, I'm going to find the tangent line at the point 2, 4, sorry, 2 ln 4. So 2 natural log of 4 and 1. Is that right? Yes, 1. 2 ln 4, 1. Now, if you look at that point, 2 ln 4, 1, well, what is t in that case? So first of all, we can find t. We can start there. Actually, I'll do this in blue to, this is the actual solution. So to find t, we have x equals root t squared plus 3. That has to equal 2. Y is equal to ln of t cubed plus 3. That has to equal ln of 4. And z is t, and that has to equal 1. Okay, well now it's quite easy to see what t has to be. It's basically spelled out in the z term. T equals 1. All of this tells us that t equals 1. So that tells us what the time value is that we're looking for this term. So let's actually calculate r prime. So what is r prime? R prime of t in this case, you basically just do exactly what we did before. You just take all of the derivatives as usual. The derivative of square root of t squared plus 3 comes out to t over root t squared plus 3, it turns out. I plus 3t squared over t cubed plus 3 j plus k. Because differentiate t with respect to t, just get 1. Now that tells you that r prime of 1 is going to be 1 over root 4 I plus 3 over 4j plus k, or if you prefer, and you should prefer, 1/2 I plus 3/4 j plus k. Please excuse the fire truck. So so that's what our velocity vector is in that case. And that tells us that, and we know what our point is. The point is 2 ln 4, 1. So what we have is x equals 2 plus 1/2 t. Y equals ln 4 plus 3/4 t, z equals 1 plus t. And that would be our tangent line. Now, I also want to spend some time working on integration. Now, integration of these things can be a little bit challenging for some folks, so I want to spend some time working on that as well. So let's take a look. So integration in this case is kind of similar to differentiation. It's basically the same notion in the sense that we're just doing the same integration from Calc 1 just several times over. So let's say, for example, we're integrating from 1 to 4. We're going to integrate the function 2t to the 3/2 I plus t plus 1 root t k dt. And this is a relatively straightforward thing to integrate. Just integrate the first term. What's that going to be? 2t to the 3/2. Well, just integrating as usual, 2 times 2/3 is going to be 4/3. Excuse me, no, that's not quite right, is it? It's 4/5, isn't it? Right, 4/5 t to the 5/2 I plus, and now in this case you have to take them both at the same time. So t root t is t to the 3/2. So in other words, that's going to become it's going to become 2/5 t to the 5/2 plus 2/3 t to the 3/2 k. I think that's right. Yep. Evaluated from t equals 1 to t equals 4. So we're going to do this. What do we find? Well, as you integrate that, as you just take both sides of this, the t term, that's going to become 4/5. 4 to the 5/2 is 2 to the 5th. 2 to the 4th is 16. To the 5th is 32. So it's going to be 32 minus 1 plus, sorry, I plus 2/5. Again, 32 minus 1 plus 2/3, 8 minus 1. Okay. 31 times 4 is 144/5, so it's 144. Is that right? That can't be right. No, 124, excuse me. I thought that didn't make any sense. So it's 124/5 I plus, in this case, that's 2 times 31, so 62/5 plus 14/3. Okay, and that's I'm just going to leave it as that for now. I'm not going to bother adding the fractions together. It's fine to leave something like that. So, and that's the integral. That's basically all there is to it. It's not very difficult in that sense, but it's good to go over some important fundamental trig and other kinds of tricks to do these kinds of problems. So let's do another example of this. What if we have, say, what if we have, let me see, what's a good one? What if we take the integral from 0 to pi/4 of secant t times tan of t I plus t cosine 2t j plus sine squared of 2t times cosine 2t. Actually, I'm going to clean that up just a little bit to reduce ambiguity. Cosine of 2t, cosine of 2t. Okay. Now, as you're doing this, it's tempting to just try to slay the dragon and do all three of these pieces simultaneously, but these can be big integrals to do. So there's no shame in taking it piece by piece. So let's look at each term individually. So let's start with the I term. The I term, we're going to anti-differentiate this, 0 to pi over 4. Secant t times tan t dt. Well, that's the same thing as the integral from 0 to pi over 4 of sine of t over cosine squared of t. And now we recognize this is a basic u substitution, where we're going to let u be cosine t, and du, in that case, becomes negative sine t dt. So this whole thing, in other words, becomes the integral from, I'm going to write t equals 0 to t equals pi over 4 to avoid ambiguity, so remember what our variables are. Sine of t, in this case, so that's going to become negative 1 over u squared du. And because of that, now that's just a basic u substitution. We know what that is. That's 1 over u from t equals 0 to t equals pi over 4. Or in other words, that's just secant, 1 over cosine. So secant of pi over 4 minus secant of 0. Secant of pi over 4 is root 2. Secant of 0 is 1. So this whole thing becomes root 2 minus 1. That's the I term. So far, so good. Let's take the j term. Integral from 0 to pi over 4. T times cosine 2t dt. This is not an obvious u substitution. This I think the best way to do this is by parts. So we're going to use the old trick that integral u dv equals uv minus integral v du. In this case, we're going to let u is going to be easy to differentiate. So the easiest thing here to differentiate, I think, is just t. So dv becomes cosine of 2t dt. So v, in other words, is 1/2 sine of 2t. du is just dt. So this becomes t over 2 sine of 2t, again from 0 to pi over 4, minus 1/2 integral 0 to pi over 4 of, let's see, where were we? So du times v, in this case, is just sine 2t dt. As you're doing this, in other words, so sine of 0 is 0. So the first term over here becomes pi over 8 times sine of pi over 4 is root 2 over 2, or root 2 over 16, in other words. So now that we know that, that's minus 1/2, and in fact, it's going to be minus 1/4, just anti-differentiating this next term. So plus 1/4, in fact, plus 1/4 cosine of 2t from 0 to pi over 4. Cosine of 2t, oh, wait a minute, I messed up, didn't I? Because it's sine of pi over 2, right. Sine of pi over 2 is 1, because it's sine of 2 times pi over 4. So it wouldn't be pi over 8 times root 2 over 2, it would just be pi over 8 times 1. My bad. So let me get rid of this guy. That's just pi over 8. Whoopsie. Plus 1/4 cosine 2t. Pi over 4. Now, cosine of pi over 2 is 0, so that just becomes pi over 8 minus 1/4. That's what I wanted to say. So that's the j term. So you have to do that one by parts. Obnoxious? Not terrible. one more, and that's the k term, sine squared 2t times cosine of 2t. I'll write that down again. It's the integral from 0 to pi over 4 of sine squared 2t times cosine of 2t dt. And that, as you're going through this, what's that going to be? Well, that's another u substitution. In this case, we're going to let u equal cosine of 2t. du is going to be negative 1/2. Excuse me, why would I say 1/2? Why am I being silly? Negative 2 sine of 2t. I'm sorry, I'm doing this backwards. Let me start this again. I'm being very silly indeed. Let's try that again. U is sine of 2t. du is 2 cosine of 2t, which means this whole thing is going to become 1/2. Forgot the dt. So this whole thing becomes 1/2 integral from t equals 0 to t equals pi over 4 of u squared du cosine 2t dt. So what's that going to be? That is going to give us, so you've got your cosine of 2t there. Everything checks out. So this becomes 1/6 u cubed, evaluated from t is 0 to t is pi over 4. Since this is since this is sine of 2t, that's going to become sine of 1/6 sine cubed of, I'm only going to write pi over 2 here since sine of 0 is 0 and sine of pi over 2 is 1, so that's just 1/6. So at the end of the day, that's the k term. So the whole thing is just the sum of all of these things. So the integral 0 to pi over 4, whole thing together, all together now, that was secant t times tan t I plus t times cosine 2t j plus sine squared 2t cosine 2t k. You do that whole thing, and it comes out to root 2 minus 1 I. And I've already forgotten what the j term was. Let me go back. The j term was pi over 8 minus 1/4. So plus pi over 8 minus 1/4 j plus 1/6 k. We've done each piece individually. My point here is there's no harm and there's no shame in taking this step by step by step and taking this nice and slowly and methodically. That is perfectly fine. There's nothing wrong with doing it that way. Now, I want to do a few more examples of these integral. I want us to all be very comfortable and familiar as possible with the integration techniques that we expect you to be familiar with and we expect you to recognize. So I'm going to continue on with some of these other kinds of examples. Let's do another one. What if we have the integral from 0 to 1 of 1 over 1 plus t I plus 1 over t squared plus 1 j plus t over t squared plus 1 k. Now again, we can separate them individually, so there's nothing wrong with that. Let's start with the I term. Integral from 0 to 1, 1 over 1 plus t dt. Now, you can kind of do this with the u substitution if you wanted to, if you really wanted to be precise about this, but maybe you don't even have to. I suppose you could say u equals 1 plus t, and du, in other words, would just be dt. And if you did that, that would turn this into the integral from 1 plus t. So it'd be 1 to 2 of 1 over u du, which in other words is ln of u from 1 to 2, which is just ln of 2. So that's not very hard at all. Just basic u substitution. The j term is not as obvious. Integral from 0 to 1 of 1 over t squared plus 1 dt. Now, if you don't remember what this is, you might be looking at that and you say, well, I kind of want to do this as a u substitution, but what's the obvious thing to substitute? There isn't really an obvious thing to substitute in this case, and you can't really easily do it by parts either, or you'll be going in circles. This is one of those special integrals that you can reconstruct this if you really wanted to. You can go through a trig substitution to do this, but you don't necessarily have to do that either. This is one of these classical integrals. It turns out that's arctangent. So that integral is the derivative of arctangent. So that's arctan of t from t equals 0 to t equals 1. Sorry, 1, not 0. Now, arctan of 1, inverse tangent of 1, what angle gives you a tangent of 1? Opposite equals adjacent, so that's going to be pi over 4. Minus, and arctan of 0 is 0, so that just becomes pi over 4. And the k term, now this one you don't need arctan for, because even though you've still got the t squared plus 1 at the bottom, you have a t in the top, so you can do this one by u substitution. U in this case would be t squared plus 1. Du would be 2t dt. So this whole thing would become 1/2 integral of, now t squared plus 1 for 0 to 1, that would be from 1 to 2 in that case, changing the bounds in accordance with u now, of 1 over u du, and that would become 1/2 of ln of u from 1 to 2, or in other words, 1/2 ln 2. So the answer in this case, integral from 0 to 1, 1 over 1 plus t I plus 1 over t squared plus 1 j plus t over t squared plus 1 k dt. That's just going to become ln 2 I plus pi over 4, excuse me, pi over 4, not k, j, plus 1/2 ln 2 k. There's our final answer. Let's do another one. What if we have the integral of the indefinite integral of secant squared t I plus t times t squared plus 1 cubed j plus t squared ln t k dt. Again, we can take this piece, but now we could take this piece by piece, and we probably should. Let's do the I term. Integral of secant squared t dt. Secant squared is one of these classic functions, again, that we should recognize. That, it turns out, is the derivative of tangent. And I think you can do it using integration by parts if you really wanted to, but it's tangent. The important thing to recognize is that's just tangent in this case. So secant squared t, that becomes, actually, I'm not even sure if you could do that by parts in an obvious way, but that's the derivative of tangent. So that's just tangent t plus, I'm going to call it C1, and you'll see why I'm doing it C1 in a second. The j term now, this is the integral of t times t squared plus 1 cubed dt. Now, you can undo that and pull apart all the algebra and expand that and then just do the anti-power rule again and again. But I think it's easier in this case to hit that with u substitution. In this case, u would be t squared plus 1. Du would be 2t dt. So that becomes 1/2 integral of u cubed du. I think that's easier. I really do. I think that's a much easier way of trying to solve this thing. So what is that? That's going to be 1/2 times 1/4, or in other words, 1/8 u to the 4th plus c2, or in other words, 1/8 of t squared plus 1 to the 4th plus c2. Why c1 and c2? Well, remember when you do an antiderivative that's indefinite, the indefinite integral, you have to add an arbitrary constant at the end of that. Now, we're just doing 3 different antiderivatives. There is nothing to say that those arbitrary constants are the same. In fact, they very likely won't be. So we have to allow for the possibility that there are different constants in each case. Let's do the k term. And what's this? Integral of t squared ln t dt. This, I think, the best way of doing this one is, again, by parts. Let's say that u is an easy one to differentiate. So the easy one to differentiate, I think, is going to be ln t. So that dv is t squared dt. V, or du rather, in that case, is just 1/t dt, and v is going to be 1/3 t cubed dt. It's easier to differentiate ln t than it is to anti-differentiate ln t, so we're going to make ln t be our u term. That's going to make this whole thing 1/3 t cubed ln t minus v du in this case, so in other words, minus 1/3 integral. V du is just t squared dt. It's t cubed over t, or just t squared. So this one's much easier to work with. 1/3 t cubed ln t minus 1/9 t cubed. Will give us the 1/3 t squared plus c3. Very good. Very good. Okay. So at the end of the day, that gives us our final answer, integral of secant squared t I plus t times t squared plus 1 cubed j plus t squared ln t k dt. And we've just discovered that that whole thing comes out to, now there are a couple ways you can write this. One way is the way I just did with the C1, C2, and C3 in each term. But the way I'm going to do that instead is I'm going to write this as the vector tan t 1/8 t squared plus 1 to the 4th. Oops, sorry. And 1/3 t cubed ln t minus 1/9 t cubed plus a vector c. The vector c is a constant vector. This guy is, I'm just declaring to be C1, C2, C3. And there's nothing wrong with writing this in either of these two ways, but I want to illustrate that this is another way that you can do this. Writing it with a big fat plus c on the end there. I want to do one more of these. So the last one of these that I want to do is, let's see if I can find it now. Okay, here it is. So integral of t e to the 2t plus t over 1 minus t, oh, sorry, that's I. I'll just write the whole thing again just to make it cleaner. I plus t over 1 minus t j plus 1 over root 1 minus t squared k dt. Now, how might we go about doing this? Well, we've got a couple options here. Again, let's go with each term individually. So the I term is going to be, so the I term integral of t e to the 2t. Again, you have to do this one by parts. Let's say that u is going to be t, so du is just dt. dv is e to the 2t dt. V is 1/2 e to the 2t dt. So that's going to be 1/2 t e to the 2t minus, now it's v du in this case, so minus 1/2 integral e to the 2t dt. So that just becomes 1/2 t e to the 2t minus 1/4 e to the 2t. If you prefer, you can write this whole thing, oh, I forgot something important, plus c1. If you prefer, you can write this whole thing as 1/4 times 2t, oh, sorry, let me try that again. 1/4 e to the 2t times 2t minus 1. If you prefer, you can write the whole thing in that way to make it a little bit cleaner, plus c1. Okay, so there's the first bit. How about the second bit? So the second thing, and that all looks fine. So the j term is a little tricky. There are a couple ways you can do this. You could try doing it by parts. And if you did it by parts, what would that look like? Well, I suppose you can have it be, you can differentiate t, and so u is t, and dv is 1 minus t. But then you'd be integrating, the problem is if you did, you'd be integrating natural log, which is not super easy, not impossible, but not super easy. There are a couple ways we can do this, though. One thing we can, let's try it both ways. So you can either do u equals t, so du equals dt, dv equals 1 over 1 minus t dt, v equals, in this case, it would be negative ln t, negative ln of, negative ln of 1 minus t. So that would be negative t ln 1 minus t plus, because you've got a negative now, plus integral of ln 1 minus t. But now you have to deal with the integral of ln of 1 minus t, which is not terrible, but you might not remember what that is. But it turns out that if you take the integral of ln t dt, that just becomes t times ln t minus 1, in which case this whole thing would become negative t ln 1 minus t plus, in this case, this would be t minus 1 times ln 1 minus t minus 1. And after cleaning that up a ton, and I mean a ton, this would become negative ln 1 minus t plus 1 minus t, after having gone through all that hubbub. That's one way of doing this. And of course, you still have to include the plus some arbitrary constant c2. Some people won't include the 1, by the way, because of that arbitrary constant c2. They can just absorb the 1. But anyways, another way of doing this is you could also write this as the integral of t over 1 minus t dt. Turns out, if you're very clever, you can write this as t minus, as the integral of t minus 1 over 1 minus t, that's just negative 1, plus 1 over 1 minus t, which is the same exact thing, dt. First term becomes negative 1. So in other words, this is the integral of negative 1 plus 1 over 1 minus t dt. And that's just negative t, negative t minus ln of 1 minus t, and plus c2. It's the same exact thing, basically. You've got a plus 1 in the other term, but again, you've got an arbitrary constant, so who cares? And the k term. Again, this is one of those integrals that you could do with a trig identity, but you might also just remember this. The integral of 1 over root 1 minus t squared dt, turns out that that's just arcsine of t. So the whole thing becomes, at the end of the day, after having done all of this, let me write it the other way, 1/4 e to the 2t times 2t minus 1 plus c1, comma, negative t minus ln 1 minus t plus c2, and arcsine t plus c3. And that's our final answer. So these are a handful of the really important trig identities and trig and trig stuff that we expect you to remember. This one was particularly challenging. So the j term and the k term here were a little bit tricky, but definitely integration by parts is fair game. Arcsine, arctan integrals, those are fair game. Secant squared, you should know what that integral is. So if you're rusty on some of your integration, then take some time to review that stuff, and feel free to ask questions on Piazza or in these recitations, or whatever you want us to help you out with. Okay, so let's go along. Now, by the way, as we're doing these integration problems, as we're doing these kinds of integration problems, this might be the last thing I do today. As we're going through these integration problems, one thing that you'll often find is you'll have to do something where it's like, oh, I don't know, let's suppose that we have to find r of t, given that we know that r prime of t is equal to ti plus e to the t j plus t e to the t k, and that r of 0 is I plus j plus k. So how do you do that? Well, this invokes the fundamental theorem of calculus, and there are really two ways of doing this. So here's strategy 1. This is, so strategy 1 is that r of t, we know this, r of t is going to be the integral of r prime of t dt plus some constant vector. I don't know what that constant vector is yet. We'll figure it out. If you just take the antiderivative itself, the antiderivative of t, that's just 1/2 t squared I. Antiderivative of e to the t, that's just e to the t j. Antiderivative of t e to the t, that's going to, again, you would have to do that by parts, but I'll let you know what that is in this case. That's going to, that's going to be e to the t times t minus 1. Okay. Plus some constant c. Now we know that r of 0 is I plus j plus k. So what that tells us is if we plug r of 0 in here, we're going to get 0 for I and 1 for j. So that's j minus k, right? Why minus k? Because you plug in 0 to e to the t times t minus 1. That's 1 times negative 1. So j minus k plus c, that arbitrary vector. But really, we know that that's going to be I plus j plus k. We're told that. And that tells us that c is I plus 2k. So now we know what our constant vector is. It tells us that r of t is 1/2 t squared plus 1 I plus e to the tj plus e to the t times t minus 1 plus 2. Okay. And there's our answer. That's one way of going about doing these things. Here's another way, which is effectively the same thing under the hood, just done in a different order. We can use the fact that by the fundamental theorem of calculus, that old friend, that using the fundamental theorem of calculus, we may recall that r of t minus r of 0 is the integral from 0 to t of, I have to make up a different letter in this case, r prime of u du. I can't use t again because t is already in the limit of integration. But what does that mean? That means that r of t minus I minus j, sorry, let me put that a different way. R of t is equal to r of 0 plus integral from 0 to t of r prime u du. Let's figure out what that looks like. R of 0, R of 0, we actually know what r of 0 is, don't we? That's I plus j plus k. We're told that that's r of 0. Plus integral from 0 to t of, now we're going to use u instead of t, so that's ui plus e to the u j plus u e to the u k du. And to differentiate that thing, we get I plus j plus k, that's our r naught, plus the, in this case, this is 1/2 of, this is 1/2 u squared, I, from 0 to t, plus e to the u, again from 0 to t, plus e to the u times u minus 1 from 0 to t. So you do that, and you get I plus j plus k plus 1/2 t squared I minus 0 plus e to the t minus 1 j plus plus e to the t times t minus 1 minus, now here's the important thing here, you plug in, or rather plus 1, okay, after you actually do the anti-differentiation. And you add everything together, what do you get? You get 1/2 t squared plus 1 I plus e to the t j, the negative 1 and the 1 with the j cancel out, plus e to the t minus 1 plus 2. Okay, that's the same exact thing that we got before, same exact answer. Now here's where a lot of students make mistakes. So first of all, hopefully you're all convinced that these give us the exact same answer and there's no difference. But oftentimes students will make the common mistake. So here's a mistake that students make. It is usually not the case that this c is equal to our initial value. Keep in mind that our initial value, that's c, the thing that we added to it, let me phrase that another way. It's i.e., here's where this really stings you. It's not true that r of t is not equal to r of 0 plus the general antiderivative of r prime of t dt. That is not what this says. This is the definite integral from 0 to t, not the antiderivative, not the general antiderivative. So keep this in mind. These two objects here are not saying the same thing. So, and it's subtle, but it's important to recognize this. I generally like strategy 1 more personally. Dr. Roberts prefers strategy 2, I think, a lot. It's a matter of taste. It's really, neither of us is right or wrong about this. It's really just a matter of taste in terms of what's the more personally satisfying. Strategy 1, I think, is a little more intuitive and a little easier to work out, why, where that C is coming from. But the notation is a little bit hand wavy and it's not as rigorous. Strategy 2 is much better notation in a lot of ways. So it's up to you which one of these you want to use. You can use either, both. It doesn't matter. But just make sure that you're not just adding R naught to whatever you find as your antiderivative, because that generally is not true. Okay, so I will stop this particular session right now and pick it up with part 2, which will be about a little bit about arc length and curvature.